Okay, so welcome to Math 310, Introduction to Modern Algebra. And so what we're going to do now for the last few classes is just talk about what I consider at least some fun topics related to what we're doing. If there are things that you want to see, let me know. There is way more in this book than can be done in one semester. There's more than can be done in 2 semesters. And so we have to pick and choose. There's a lot more you can do with groups, with rings and whatnot. I want to try to give you a sense of some of the advanced mathematics that's lurking behind this and why you might care about some of this. So the main thing I want to do today is talk about infinities. Okay. Whenever you see an infinity, this should be a warning light, siren flag, whatever. Danger sign. You have to be careful how you deal with infinities. Okay. Frequently, infinities are not dealt with properly. People are very cavalier in terms of how they deal with them. And so I want to try to do some fun examples to just show you how careful you have to be. Okay, so the first is, have we done the Hilbert Hotel before? Not so easy to build, but so imagine every room is booked. And there are infinitely many rooms. Each room is a different natural number, 1, 2, 3, 4. Okay, so every room is occupied. And someone comes in and says, I really need a room tonight. I'll give you $1 million. Manager is going to want to squeeze them in, but every room is filled. And nobody wants to share a room with someone else. Otherwise, of course, you just pile them up. So how can you get one more person in if every room is filled? So every room is filled and we want to get another person in. Any thoughts on what we can do? So we have infinitely many rooms. If we had only finitely many rooms and somebody else comes in, is there anything we can do? No, we're stuck. But with an infinite amount of rooms, there's actually some possibilities. What if we shift everybody 1? So we move the person who was in room 1 to room 2. We move the person in room 2 to room 3. This is, of course, inconvenient for them, but we don't care. We're getting $1 million. We move the person from room 3 to room 4. We move the person from room 4 to room 5, and so on. And so when we do this, we have now opened up a new room. And now we can put in a new person. So even though every room is filled, we were able to get somebody else in. Could we get 2 people in? Yeah. Lather, rinse, repeat. Can we do any finite number? Yeah. So could add 2 more, 3 more, ... n more. Could we add infinitely many more? Any finite number, sure. Can we do infinitely many? How?
So I guess you just send the guess to the number multiplied by 2. So all the
excellent. Send n to 2n. So we could get infinitely many more people to be added. So before I do the next one, let me just add. You should have seen, if I have the derivative of 2 functions, it's the sum of the derivatives. What if I have 3 functions? What's the derivative of the sum of 3 functions?
The derivative of each sum.
The derivative of each. So the derivative of a sum is the sum of the derivatives. Did you prove this in your calculus class? I'm afraid to ask if you even proved the first one. So the way you prove this is we say, well, it's the same as f plus g plus h and take the derivative. Now we have the derivative of 2 functions. So now that is the derivative of the first, which is f plus g, plus the derivative of the second. And now that's f prime plus g prime plus h prime, and now we just drop the parentheses, because the parentheses don't matter. So if we know the derivative of a sum of two functions is the sum of the two derivatives, then we can get the sum of 3, then we can get the sum of 4. What are we technically using here? What's the proof technique?
Induction.
Induction. So this is an induction argument. So if no, the derivative of a sum of two functions is the sum of the derivatives, then the derivative of sum of functions is the sum of the derivatives. Do you think there's anything I have to be careful about?
Finite sum.
Yeah, there's a big space there, right? So any of a finite sum. So if everything is finite, we're okay. When we're doing things by induction, a finite sum is no problem. What about an infinite sum? Should the derivative of an infinite sum be the infinite sum of the derivatives? Can we just take the limit? For any finite number, we're okay. So should we all be okay in the limit? So let's consider f of x equals the sum, n goes from 0 to infinity, of the sine of 4 to the n x divided by 2 to the n. Okay. So here is a function. Does this function converge? What do you think? So again, I'm now calling on you to remember some results from previous classes. What do you think? Do you think the sum converges for all x? Yeah, what can you tell me about the numerator? How large is the numerator in absolute value? Yes, at most 1. At most 1 in absolute value. So this converges by the comparison test, with just, the sum of 1 over 2 to the n. So not only does it converges easily. This is not hard. So imagine we could differentiate term by term. If f prime of x is the sum of the derivatives, then what would f prime of x be? So what's the derivative of sine of the quantity 4 to the n times x? What rule do we use to take the derivative of sine of 4 to the n x? You can use 2 different rules.
General.
Chain rule is one, and the other one?
U sub.
Could you use a multiple rule? If you really how we're a glutton for punishment, you could write
Yeah, that's.
4 to the n
nasty.
x as x plus x plus x plus x plus x plus x plus x, and use trig identities.
Yeah, that would be nasty.
So if we use the chain rule, derivative of sine is cosine. So you'd get cosine of 4 to the n x, and then the derivative of 4 to the n x. What's the derivative of 4 to the n times x? 4 to the n. We divide by 2 to the n, and so this is going to be the sum, n goes from 0 to infinity, of 2 to the n cosine 4 to the n x. Do you think that's the derivative of the function? So if we differentiate term by term, that's what we get. Do you like this function? The sum of 2 to the n times cosine 4 to the n x. Why not?
Give it those up to.
Yeah. At x equals 0, we get infinity. So each function, each summand is differentiable. Each individual piece is differentiable. When I sum them together, I get a function. Either the function is not differentiable, or if it's differentiable, its derivative is not the sum of the derivatives. Either way, this example proves that the derivative of an infinite sum is not necessarily the infinite sum of the derivatives. It is possible that the function is not differentiable, or it's possible that the derivatives of something else, and these are not legal. You have to be very careful whenever you have an infinity. For any finite sum, we're okay. And it turns out there's a whole theory behind functions like this. This should distress you a little bit. And a lot of math books use things like this, where you have a continuous function that is differentiable nowhere. And so there are ways to construct functions like this and to show that in some sense, most functions are differentiable nowhere. We work really hard to give you nice functions that we can work with. We work really hard to give you functions that have nice antiderivatives. Most of the time, that's not the case. It's good to be aware that stuff like this exists. Okay, this is just a real warning of infinity. The reason I want to do this is a lot of what we've done this semester is we've worked with finite groups. And you have to be really careful about pushing what you know from finite to the infinite. All right. Has anybody seen the following banking problem? So we're going to start at time 1/2, and then the next step will be at time 3/4, 7/8. So we're going to do infinitely many transactions before 1 second passes. Okay. A little bit unreasonable to physically imagine such a situation, but we are taking an upper level math class. We can look at this theoretically. So we're going to be doing a tremendous number of transactions. I will give you a choice as to which way do you want to be. And you will be Bob. Okay. So in the first variant, in both variants, at the nth time step, Alice gives Bob a dollar bill. And the first, she gives the dollar bill labeled 1. In the second, she gives the dollar bill labeled 2. In the third, the dollar bill labeled 3. In the nth, the dollar bill labeled n. So Alice's bills are labeled 1, 2, 3, 4, 5. At the nth time step, she gives Bob the bill marked n. Okay? In the first variant, at time step 10 to the n, Bob gives Alice back the lowest numbered bill he has, and Alice puts that in a safe. In the second, Bob gives Alice the 2 highest numbered bills he has, and Alice puts that in a safe. You are Bob. Which would you rather do as Bob? Give Alice back the lowest numbered bill that you have, or give Alice back the 2 highest numbered bills that you have? It's okay if you're wrong. What does your intuition say? As soon as you see this, which is So you think it's better to give one bill back as Bob than giving back two? Seems reasonable, right? At any finite moment in time, if you're Bob, will you give Alice back more money in method one or more money in method two? At any finite moment in time, you're going to give back twice as much money to Alice in variant two. Right? Because every time we do a transaction, in the first variant, Bob gives Alice back the lowest bill. In the second, Bob gives Alice back his two highest bills.
So that's for each time step.
For each time step.
Okay.
Right? So doesn't it seem like it would be better for Bob to do variant one and just give back the lowest? Okay, we're going to see who has been paying attention all semester. Who wants to be Bob and do variant two? So you want to do that. You want to give back twice as much money.
So my idea is that they're going to be along 1 second, the number of transactions in the first half of that second is going to be comparatively significantly smaller than the second half. More number of transactions.
But at every finite moment in time, in the second method, Bob is always going to give back twice as much as in the first.
The higher bills would have been taken care of in the first half.
Okay, so let's look at what's going on. So variant one, variant two, and then we'll do time up here. So 1, 2, 3. And so let me just see how we want to label things. And we'll do Bob and Alice is safe. Bob and Alice is safe. 1, 2, ... 9, 10, 11, 99, 100, 101, ... 999, 1,000. Okay, so at time one, Bob gets $1 in both methods, right? Because Alice gives Bob $1. At time two, gets another $1. So now Bob has 1 and 2, 1 and 2. At time 9, Bob has 1 through 9. Now at time step 10, Bob has 1 through 10, but then he has to give back 1 to Alice is safe. So now Bob has 2 through 10, but Alice is safe has 1. In the second method, Bob has 1 through 8, and Alice is safe has 9 and 10. Everybody comfortable with that? Now, when we get to 99, Bob is going to get bills 2 through 99, and Alice is safe has 1. Down here, Bob has 1 through 8, and then 11 to 99, and Alice is safe has 9 and 10. And now let's see what happens. Now, at time step 100, Bob gets bill 100, and what does he give to Alice? He gives 2. So Bob now has 2 to 100, and Alice has in her safe 1 and 2. Down here, Bob has 1 to 8, 11 to 98, and gives back 99 and 100. So Alice now has 9, 10, 99, and 100. If we were to do this again, when we get to 1,000, Bob would have 3 to 1,000, and Alice is safe would have 1, 2, and 3. Down here, Bob would have 1 to 8, 11 to 98, 101 to 998, And down here, Alice's safe would have 9, 10, 99, 100, 999, 1000. So we can see in the second variant, Alice has much more money in her safe. She's got twice as much money. Doesn't it seem like the second method is better for Alice and worse for Bob? So who would like to be Bob in variant 2? Who would like to be Bob in variant 1? You've got to choose. Which Bob do you want to be?
Variant 2.
Variant 2. Is there anybody who would rather be Bob in variant 1? So variant 2 means you are giving more money back to Alice.
I don't trust it.
So you've taken enough classes with me that you know by now something is fishy.
Something's going on.
Something is going on. You know, I volunteer a lot in elementary schools, and by the time the kids were in, I think it was 4th or 5th grade, I had come in so often, they knew whatever I was proposing. There was some con, there was some trick to it. Notice that in the first variant, Alice gets back her bill 1, and then Alice gets back her bill 2, and then Alice gets back her bill 3. What's the next bill Alice is going to get?
4.
And the next bill Alice is going to get
5.
every bill that Alice gives out, she gets back. In the second variant, once we get to time step 10, Bob is never going to give back bills 1 through 8. Once we get to 100, Bob is never going to give back bills 11 to 98. Once we get to 1,000, Bob is never going to give back bills 101 to 998. So the difference between the two methods is, in the first method, Alice gets everything back. In the second method, Bob actually keeps infinitely many dollars. It seems worse. At every moment in time, it's worse for Bob. Bob is giving back more money at every moment in time. At every moment in time, he has less money in method 2 than method 1. And in the limit, method 2 is better for Bob. So method 1, Alice gets all back. Method 2, Bob keeps infinitely many bills. So this is a strange situation where at every finite moment in time, you're doing worse, and in the limit, you're doing better. So these are great examples. Again, some of you have said that you're going to be teachers. These are things you can do with young kids. We're not using much advanced mathematics. Physically, can you do this? What would it mean to be doing this many transactions, to doing infinitely many transactions in 1 second? We don't have any way to physically do that. Formally, we can look at this. And this just hopefully shows you some of the dangers of working with infinities. Okay, how many of you have not seen the words countable and uncountable? Everybody has seen countable and uncountable. Okay, so countable means you have the same size as the integers. Uncountable is larger. Okay. So countable, same size as the natural numbers or the integers. Uncountable, it's larger. Does anybody know what number or what letter we use to represent the size of the natural numbers?
Aleph.
Aleph not. And it's responsible for the longest song in the English language. Aleph not bottles of beer on the wall. Anybody know what we use for the cardinality of the reals? It depends. It is actually independent of the other axioms of set theory. So it would be natural if the reals are the smallest infinity larger than the rationals. But you can either assume that, or you can assume that there is something in between, and if set theory was consistent before, it will still be consistent. So the person who finished the proof of that was one of my mathematical grandfathers, Paul Cohen. And so he was the one who showed that if set theory is consistent, it can be Aleph 1 or it can be something else. It is not too bad to show that the real numbers are definitely larger than the rationals or the integers, that there is a, that's a strictly larger infinity. And again, I don't want to go into too much set theory right now. How many of you have taken a class in set theory? If you're going to be a mathematician, at some point you should take a class in set theory, at some point you should take real analysis, at some point you should see Dedekind cuts, and then you should almost never see it again. But just at one point in your life, you should see, how do you do all of this rigorously? How do you build all of this up? So if I give you the rationals, one way to show that they're countable is I can actually, there should be a nice fast way to quickly make a grid. And so what I'll do is, I'll put my numbers here, 0, 0, 1, 0, 2, 0, dot, 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 0, 1, 1, 1, 2, 1, dot, 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 0, 2, 1, 2, 2, 2, dot, dot, dot. And the point AB will correspond to the fraction A over B if B does not equal 0. And so there's a couple of ways I can now walk through. Every rational number is going to be on this list. Clearly, the rational numbers can't be smaller than the integers in size because the integers are rational numbers. All we have to do is show that the rational numbers can't be larger, that there's a one-to-one correspondence between the integers and the rational numbers. So one way you can do it is you just walk through diagonally. And you just take all the numbers that are new. So when I get to the number 2, 2, I don't bother taking that because I've already gone in 2, 2 with the number 1, 1. When I get to 0, 2, I don't bother taking that because I already got 0 from 0 slash 0, comma 1. So that's one way to walk. Another way that people sometimes walk is they sometimes go in right angles like that. There's lots of different ways to go. The main thing is if you want to explicitly write down what the correspondence is, which is easier to do, lines or right angles like this in terms of, I'm like filling out squares. So that might be easier to make things explicit. In general, this is an example of a situation where you don't want to make things explicit. You want to basically say, you can see that there's going to be a correspondence, that if you give me any rational number, I know eventually I will walk and I will hit it. So there's a one-to-one correspondence. I know when I'm going to hit it. Okay, so the rationals are countable. We just showed that the rationals were countable a moment ago. And what's nice is a countable union of countable sets is countable. And so if I have countable union of countable sets, well, what I can do is each set can be put into one-to-one correspondence with the integers. So you put your first set down here, you put your second set above it, you put your next set above that, and then you just walk through it as we talked about a moment ago. You maybe walk through like this. And so if I have a countable union of countable sets, it's going to be countable. The reals are uncountable. How many of you have seen a proof that the reals are uncountable? Most of you have not seen this. Okay. this is worth seeing. So it's enough to show 0, 1 is uncountable. So we just have to show that that can't be put into a one-to-one correspondence with the integers or the rationals or the natural numbers, something like that. So given any x in 0, 1, we can write x, and we can either do things in binary or in decimal. You're going to be a little bit careful. Let's write it in binary. So it's going to be dot x1, x2, x3, x4, dot, dot, dot. Each xi is in 0, 1. Does every number have a unique binary representation?
Yes.
So if I give you 1/2, how would you write 1/2 in binary?
Oh, it's been too long.
Well, how would you write 1/10 in decimal?
0.1.
0.1. How would you write 1/2 in binary?
0.1.
It's 0.1. 0.1 just means I have 1 in the 1/2 spot. What about 3/4? That would be 1/2 plus 1/2 squared. That would be 0.11. Unfortunately, 1/2 also equals 1/4 plus 1/8 plus 1/16 plus 1/32 plus dot, dot, dot. So it's 0.01111 dot, dot, dot. So we actually don't have unique representations. Yes,
That not also true in base 10 with 0.99.
it is also true in base 10.
Yeah, so then why, if that's not a problem in base 10, why?
Oh, no, this would be an issue in base 10 as well, is that certain numbers have multiple representations. And so we unfortunately have to be a little bit careful about numbers that have more than one representation. And so if I give you a number like 1/2, I can actually write that 2 different ways. And so what we can do is we can make a decision. If I have 2 different ways to write a number, maybe I always choose the way that terminates. Or maybe I just have extra things on the list. There's not going to be that many. So I'm not going to go into all the details here, but you do have to deal with non-uniqueness of representation. Okay, so it's a little bit of an issue that you have to be careful about. I can write 1/2 2 different ways. So maybe you include both. And so, assume 0, 1 is countable. So list all numbers. So the first number, x1, I can write as point x11, x12, x13, dot, dot, dot. The second number, I'll write as point x21, x22, x23, and so on. The third number as point x31, x32, x33, and so on. So I have my list of all numbers. And I form a new number, x, to be point x11 hat, x22 hat, x33 hat, dot, 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 where xii hat equals 1 if xii equals 0, and 0 if xii equals 1. So I flip the ith digit. Could this number be on my list? Is it possible that x is the same as the number x1? Why not?
X11 hat will be
because it differs in the first spot. Could it be the second number on my list? No, it differs in the second spot. Could it be the third number on the list? It differs in the third spot. So the hope is X is not on our list as not Xi as differ in ith digit. What's the danger? I mean, we've definitely set it up so it can't be X1 because it has a different first digit. It can't be X2 because it has a different second digit. It can't be X3 because it has a different third digit. Well, imagine, X1 was 1/2, which is 0.1, and we write it like this. And imagine X2 is some other number, maybe it's 0.00, and I don't care what happens from this point onward. And X3, and actually, I don't even care what happens before there. And maybe X3 is, I don't care about the first two digits. Oh, wait a minute. Right. And then the third digit is a 0, and I don't care what happens. And X4, I don't care about the first three digits. The next one is a 0. So if I did that, my new number X, I change all of these digits. It would be 0.0111. And what does that equal?
1/2.
1/2. So I've got to be a little bit careful. So I'll let you fill in the details as to what can you do. If I just added both representations of 1/2, would that then be enough to then force me not to be either one of them? So I'll let you think about this. This is not a class in set theory. I'm just trying to show you a little bit of what's out there. Okay, so try to make this rigorous. Try to be aware of at least what are the complications, what are the issues. Okay. So here is a really nice result. Almost every real number is transcendental. So how many of you have seen the words algebraic and transcendental? This becomes very important as we keep going forward in modern algebra in terms of what is the structure of numbers. And so we say alpha is algebraic if it's a root of a polynomial of finite degree and integer coefficients. If you want, I could have rational coefficients, but I can just multiply through by the greatest common denominator. And then that would give me a polynomial with integer coefficients. So I might as well just assume that my polynomial has integer coefficients that alpha is a root of. So we've talked in this class about trying to find roots of polynomials. So the claim is the set of algebraic numbers is countable. So let's let an be the set of all alpha such that f of alpha equals 0 with f a polynomial of degree n and integer coefficients. Okay. The algebraic numbers clearly are the union of all these sets. Because if you're an algebraic number, you have to satisfy a polynomial with integer coefficients of some finite degree. Is it possible that the same number could be in two different ANs? Is it possible that maybe I have something that's an A2 and A5? So I'm not saying that these sets have to be distinct. Somebody give me a number that's an A2, a polynomial of degree 2 with integer coefficients. So somebody give me something in A2.
X squared,
I'm sorry?
X squared.
Well, that's a polynomial. You have to give me the numbers that are going to be the roots. So I need a
Oh,
root of a polynomial of degree 2. So that would give me 0.
0.
So 0 is in A2, right?
Mhm.
Because it is a root of x squared. 0 is also in A1, it's also in A5. 0 is in every one of these. X minus any integer, x minus 3 would be in A1. X minus 3 squared would be in A2. X minus 3 cubed would be in A3. This is not necessarily a disjoint union. If I give you a polynomial of degree 2 that has alpha as a root, if I multiply that by a polynomial of degree 5, I now have a polynomial of degree 7. So you give me anything in A1, and I can bump it up to something in A2 by just multiplying by x. So in fact, the way we've defined things, A1 is contained in A2 is contained in A3. What you could do is you could say, maybe I want my polynomial to be irreducible, that it can't factor. You know, maybe put in some kind of constraint like that. We'll just look at it like this. So we've shown that a countable union of countable sets is countable. If we can just show AN is countable, we're done. And the claim is AN is countable because if F is an AN, then that means we're given some coefficients A0 through AN, right? If I give you a polynomial of degree n, it has n plus 1 coefficients. Each coefficient has to be an integer. How many tuples do I have? I have a tuple with n plus 1 components. If it just had one component, it's just equivalent to the integers. That's countable. If it's two components, it's a union of two countable. It's a product of two countable sets. It's still countable. If I have 3, countable. If I had 4, countable. So there's only countably many tuples. So the number of tuples is countable. Each gives, at most, n roots, right? So each tuple generates at most n roots. I have only countably many tuples, so I have a union of countable sets, a finite union of countable sets that's going to be countable. So each AN is countable, so all the algebraic numbers are countable. Almost every number is transcendental. If you choose a number at random, it's transcendental. Can somebody give me a transcendental number? Pi. And give me another one. E. And then there's a lot of other numbers that we think are transcendental, but we can't prove it. To prove E and pi are transcendental is not too bad. It's one of those proofs where you can follow it line by line and have no idea why someone is doing this. It's like, okay, I understand, sure. And yes, why are you doing this? Okay, yes. And you end up getting a contradiction of you get an integer is strictly larger than 0 and strictly smaller than 1. And since there are no such integers, then you have a contradiction. So if you're interested, let me know. I'm happy to share the proofs of that. But almost every number is transcendental. Why is this important? A lot of properties are governed by the structure of the number. Integers behave different than rationals, behave different than irrationals, and different types of irrationals behave differently. How many of you are doing things in physics? So sometimes you might see whether or not certain things align and become periodic, or if they go off. And it's going to depend on some of the structures of the numbers. How many of you do things on computers? Okay. Have you ever worked exactly with pi on a computer?
No.
No, you can't. What can you only do with a computer?
Get an estimation of it.
Estimation. What does a computer work with?
Binary.
Binary, zeros and ones. You can basically just do rationals. So whatever you're doing on a computer, whenever you're trying to simulate things, you are trying to do rational approximations. And the question is your approximation going to be good enough for some of these transcendental behaviors? So you need to find a good metric. In some things, the metric is really, really obvious. We just had in baseball awards for end of the year. Who is the most valuable player? Who gets the Cy Young Award for the best pitcher? In some years, there's a lot of controversy over who gets which award, because it's not clear which things really matter. Can you give me something in sports where everybody agrees this is a good metric to figure out who's better? And you may not be comparing individuals, you may be comparing teams. Wins and losses, right? That's a pretty good statistic. When you're trying to see how good is a team. But does it matter who you've played? So college football is notoriously a challenge to evaluate because you don't have that many good head-to-head games. And so how much credit do you give beating a bad opponent? How much credit do you give just barely surviving a bad opponent? You did win, but boy, you cut it close. And so there's a lot of discussion on how do you determine the order of college teams when you can't play. In a lot of European soccer leagues, they have two levels. And in the top level, everybody plays everybody. And at the end of the season, the three worst teams go down. And in the bottom, in the next level, the three best teams go up. And you play everybody once at home, once at away. It makes it very easy to compare. So when you're trying to find a good metric, it's not always easy. If you have a playoff series between two teams, if one team wins more games, are they the better team? They got the job done, they won more games, and they get the ring, they've triumphed, but that doesn't necessarily mean they're the better team. They might have just had a couple of really lucky breaks, they might have had just a brain freeze or just made one or two bad plays at key times. And so for some things, it's not easy to come up with a good metric. If I want to try to approximate a number, I can't work with pi. I have to approximate pi with rationals. So if I wanted to get pi to a couple of digits, how could I get pi to several digits as a rational number? Okay, and how are you getting that? So there are ways to do that, but can anybody rattle off pi?
3.14159265358.
Okay, this is good enough. So how can you give me a rational approximation of pi that will give you at least 2 decimal places?
314 divided by.
Perfect. Anything wrong with this? There's something wrong with what I have written. What is what I do wrong? No, it's over 100. Yes, said it's equal to. This is one of the biggest mistakes that people make. It is not equal to. It is approximately equal to. If I want to do a little bit better, what if I want to get pi to 3 decimal digits? And maybe just do 3141 over 1,000 or 31415. And we can worry about do we want to round up or not? So does everybody agree that if we can calculate pi with its decimal expansion, we can easily find rational approximations? If I can give you the decimal expansion of pi, truncate the decimal and multiply by 10 to the n, and then divide by 10 to the n. And now you have your rational approximation. What's good or bad about this? It's easy to do if we have the decimal expansion. What's bad? God. I think I can say that at a school like this. You can be divinely inspired. There are actually formulas that calculate pi. One of my favorites. Yeah, because this is a class on infinities. Okay. So this is a calculus review. You should all know this, and I will assume none of you know this. Does anybody know the derivative of arctangent?
1 better than 1 plus x squared.
Well done. Remember to send me an email. Well done. Do you know how to prove that? So if I give you f of g of x equals x, then f prime of g of x times g prime of x equals 1. That's the chain rule. So g prime of x is 1 over f prime of g of x. So if you know the derivative of f, you know the derivative of its inverse function. This is how we go from knowing the derivative of e to the x to the derivative of natural log. So I need to find two functions whose composition gives the identity. Can you think of any function to compose arctangent with of x and get x from it? What function should I have hitting arctangent?
Tan of arc.
Yeah. So the tangent of arctangent of x equals x. Right? So by what we've just used a moment ago, that tells us arctangent prime of x is 1 over tangent prime at arctangent of x. So tangent is sine over cosine. Does anybody remember what the derivative of tangent is? What rule would you use to get the derivative of tangent?
Quotient rule.
Quotient rule. And so when you do that, you have sine over cosine. You get cosine times cosine minus negative minus sine times negative sine. So you get cosine squared plus sine squared over cosine squared. So you get 1 over cosine squared. It is secant squared, but I actually want to just leave it as 1 over cosine squared because I have 1 over tangent prime. So then that means this is the same as cosine squared of arctangent of x. Right, now it's time to draw a picture. Okay, I want the arctangent of x is what angle has a tangent of x. So if I were to draw this triangle, if I want an angle to have a tangent of x, can anybody tell me what some of the sides should be? So I want an angle, theta, whose tangent is x. Can you give me a possible triangle that would work? So what's the definition of tangent? It's opposite over adjacent, right?
Okay.
So what would be a good choice of opposite over adjacent to get x?
X over 1.
X over 1. So if we make the vertical x the horizontal 1, then that angle will have a tangent of x. So this angle here, theta, is just arctangent of x. What's the hypotenuse going to be?
Square root of 1 plus x squared.
The square root of 1 plus x squared. And now that we know this, now we can take the cosine squared of arctangent of x. The arctangent of x, it's that angle. So if I look at that triangle, cosine is 1 over the square root of 1 plus x squared. So that gives me 1 over 1 plus x squared, which is exactly what you said. So this is a proof that the derivative of arctangent is 1 over 1 plus x squared. Okay. So I think I'm going to be able to do this without making a mistake. What is the integral from 0 to 1 of arctangent prime of x dx? This is one of the easiest integrals I can give you. I'm integrating the derivative of arctangent. What do you get when you integrate the derivative of arctangent?
Arctangent.
Arctangent. So this is just arctangent at 1 minus the arctangent of 0. What angle has a tangent of 1? And remember, we do things in radians, not in degrees. Pi over 4. And what angle has a tangent of 0? 0. There was a clock in this room in the past, correct? Okay. I know, I think socks become coat hangers or something like that, or we now have a team 6 in its place. Okay, so this is just pi over 4 minus 0. Okay. But we know the derivative of arctangent is 1 over 1 plus x squared dx. This is the same as the limit as epsilon goes to 0, the integral from 0 to 1 minus epsilon, 1 over 1 plus x squared dx. Okay. I'm just going to stop just a little bit before 1. And then I'll take the limit as I get closer and closer and closer. Does anybody recognize what 1 over 1 plus x squared looks like? You've seen a sum like this before.
Is it like sigma x to the n factorial x to the x?
Not x to the infinite. Nope.
Oh, it's like 1 divided by 1 minus x.
Nope. So epsilon goes to 0. Let me rewrite it as 1 minus negative x squared dx. Where have you seen something in the form 1 over 1 minus something? Usually they use the letter r, 1 over 1 minus r, geometric series. So this would be the limit as epsilon goes to 0, integral from 0 to 1 minus epsilon, 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th dot 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 dx. This is the geometric series. Yes? Okay. So it's a geometric series where the ratio is just negative x squared. What's the integral of an infinite sum? I know I told you have to be careful, but I don't want to be careful. What would you hope the integral of an infinite sum would be?
Some of the
Sum of the infinite integrals, right? And so you can justify that here. And this is why I am being very careful. I'm going up to 1 minus epsilon. Because as long as I go up to 1 minus epsilon, I can show that in the limit, if I go very, very, very deep into that sum, eventually all the terms are going to become very negligible. Even if epsilon is really small, eventually I'm going to raise it to such a large power, it's going to become small, and I can show that the contribution is negligible. If, however, I went all the way up to 1, then when I'm trying to expand this, I'm expanding, it's 1 minus 1 plus 1 minus 1 plus 1 minus 1, and that has trouble. So this would then be the limit as epsilon goes to 0, and now I integrate. What's the integral of 1? X, and I evaluated 1 minus epsilon and 0, so that's the first term is 1 minus epsilon. The second term is I integrate x squared. So that becomes x cubed over 3. So it's going to be minus 1 minus epsilon cubed over 3 plus 1 minus epsilon to the 5th over 5 dot dot dot. And that's going to become, as epsilon goes to 0, 1 minus a third plus a fifth minus 1/7 is pi over 4, or pi is 4 times the alternating sum of the reciprocals of the odd numbers. This is not the best way to calculate pi. The series converges slowly. But I know if I stop at the minus 1/3, that's going to be a lower bound because everything from that point onward is positive. You know, if I just look at them in pairs. If I stop at the 1/5, that's going to be an upper bound because everything from that point onward. So if you want a certain number of digits, I know how far I need to go down. And if I want 1,000 digits, I can get 1,000 digits. So a little bit of a digression, but I can calculate the decimal expansion of pi. It's a little bit of work. This is not the best way to do it, but I can do it. So I can now calculate the decimal expansion of pi. So we're going back to our question, finding a good metric. And again, this is something that you can hopefully take from this class. You're not going to use most of the content, but trying to find what's a good way, what's a good comparison, what's a good statistic to use. This is one of the key points. What's potentially problematic about these approximations for pi? So if I want 2 decimal digits, my denominator is of size 2 digits. If I want 3 digits, my denominator is of size 3 digits. If I want 4 digits, my denominator is of size 4 digits. The denominators are growing. The bigger the number is, the harder it is to work with. You gave me 22/7. That's a good approximation with a small denominator. So maybe the metric is the smaller the denominator, the lower the cost. So that makes sense. The bigger denominator I have to use, the more expensive it's going to be to work with. And so I will judge how good an approximation is based on the size of the denominator. And so the question is, can I get a good approximation by using a small denominator? And so it turns out if I give you an irrational number, infinitely often, I can find a fraction, p over q, that's within 1 over q if alpha is irrational. Okay, this is not that surprising. I can't use a certain phrase because then YouTube could slap some language warning on this, but this is the no duh theorem. Right? Imagine alpha is in 0, 1. So without loss of generality, alpha is in 0, 1. Then what you do is just keep taking steps of size 1 over q. P minus 1 over q, p over q, dot, 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 dot. And then this would just be q over q, which would be 1. So if I keep walking in steps of size 1 over q, then alpha has to fall in one of these intervals. Right? And so let's say alpha falls in this one over here. Then since alpha falls in this interval, it can't be more than 1 over q away. So this is really a very unimpressive theorem. But it's not bad, but it's not that surprising. The next theorem is much better. So we've done the pigeonhole principle before, I think, in this class, or the box principle, or Dirichlet's principle. If you have, we've done this?
I've done it before. I don't know about this class, but yeah.
I think we've done this. This is one of the most important results, or one of the most important techniques we have. If you have n+1 pigeons and n boxes, and you carefully, lovingly put the pigeons in the boxes, then at least one box must have 2 pigeons. And again, this is another no duh theorem. If each box had at most 1 pigeon, and you only have n boxes, that only accounts for n pigeons. You've got n+1 pigeons. So at least one box has to get 2 pigeons. Another way of saying this is, it is impossible for everyone to be below average. At least one person has to be average. or better. So if we have n boxes and n plus 1 pigeons, then on average, each box has more than a pigeon. And because we care about these pigeons, and we're not going to take a wing and put the wing in this box and a beak in that box, you only move pigeons whole, right? At least one box has to have 2 pigeons. It is amazing how powerful this is. Here's a nice example. And again, if you like more of this stuff, I've given a link. Given numbers a1 through an that are integers, prove a subset has a sum that's divisible by n. What if there are only n minus 1 numbers? So could you give me n minus 1 numbers such that no subset of them has a sum that is a multiple of n? So what would be the simplest thing to assume about all the numbers? Because we have to look at all possible sums. So if the numbers are the same, there's going to be a lot fewer sums. And we might as well make all the numbers what? 1. Because if they're all 2 or 3 or 4, we've just rescaled things. So if a1 equals ... equals an minus 1 equals 1, no subset is a multiple of n. So if I only have n minus 1 numbers, it is possible that no subset is going to have a sum that's a multiple of n. For the pigeonhole principle now, I want to prove that there's a subset that has a sum that's a multiple of n. So when I look at the possibilities, what are the number of possibilities for what I get when I divide a subset by n? When I divide one of these sums by n? How many remainders do I have?
N.
We have n possible remainders. These are the boxes. When you're doing a pigeonhole problem, there's 2 things you have to identify. What do you think the 2 things are that you have to identify? Pigeons and the boxes, right? Just like when we were doing the orbit decomposition, the orbit theorem, orbit formula. You have to identify what is the set and what's the group acting on it. Same thing here. If I want to use the pigeonhole principle, I have to identify what are the boxes, what are the pigeons. How many subsets are there of a1 through an? So how many subsets are there? I give you n numbers. How many subsets can you form?
N factorial.
2 to the n, not n factorial. N factorial is the number of ways to arrange them. So for each number, I either take or I don't take. So there's 2 to the n possibilities. But I throw away the taking nothing, right? So there's 1 less than 2 to the n possibilities. That's a huge number of possibilities. But maybe a lot of those sums are the same because maybe some of the a's are the same. And so, if a1 and a2 are the same, then the sum of a1 and a3 is the same as the sum of a2 and a3. Oh God, that's getting complicated. What I can do is for my pigeons, I can look at a1 plus a2, a1 plus a2 plus a3, all the way down to a1 through an. That gives me n pigeons. How many pigeons am I supposed to have to use the pigeonhole principle?
N plus 1.
N plus 1. I'm in trouble. I only have n pigeons. But what I can do is I can say, assume that there's no sum that is a multiple of n. So if we assume no sum is a multiple of n, all of these go in box 1 or 2 or n minus 1. Right? I never use box of remainder 0. If there's a sum that's a multiple of n, then the problem is over, it's done, I've won. So you might as well assume that there's no sum that's a multiple of n. If no sum is a multiple of n, how many boxes do we have now? Now we only have n minus 1 boxes, and we have n pigeons. Now we're good. So say maybe a1 plus ak and a1 plus am in the same box. What does it mean to be in the same box? They have the same remainder when you divide by n. So if you subtract, you get ak plus 1 all the way to am is a multiple of n because they're in the same box. So this is a nice application of the pigeonhole principle. Okay, again, you have to figure out what are the boxes, what are the pigeons. A lot of times when you do problems like this, you can try to do like a proof by contradiction. If the property holds, great, we've won. So let's assume it doesn't hold, and now let's argue from that. And if no sum is a multiple of n, then we don't have to worry about n boxes of remainders. We only have to worry about n minus 1 boxes of remainders. This is a hard problem. This is not an easy problem. You have to figure out what are the right pigeons to look at. There are 2 to the n possibilities, or 1 less than that if we exclude taking nothing. 2 to the n is a huge number. If n is 10, 2 to the 10 is about 1,000. 2 to the 30, let's do 2 to the 100. 2 to the 100 is about 10 to the 30. That's more than the number of molecules in this room, or maybe on the order of magnitude of that. That's a huge number when n is 100. There's so many possibilities. We just have to find a very good special set. And that's the challenge, is we don't have to look at all possibilities, we just have to look at some. So I'm not going to prove this. I hate when it changes the size of the subscripts. Sorry, okay. Okay. So using the pigeonhole principle, you can actually show that infinitely often you can find a fraction whose distance from your irrational is at most 1 over the denominator squared. So if you want to get 5 digits of pi, well, let's say you want to get 10 digits of pi. You don't have to use something of size 1 over 10 to the 10. You can use something of size 1 over 10 to the 5 and still get 10 digits. If you want to get 100 digits of pi, you don't have to use a 100-digit fraction. You can do it with a 50-digit fraction. I'm not going to give the proof of this. If anybody's interested, you email me and I can show you that, or I'm happy to do a Zoom and go through. It follows from the pigeonhole principle. So this leads to a natural question. Which irrational number is the most irrational of all? So Disney or fairy tale quiz time. Snow White, people remember this one, the original? What does the queen ask the mirror? Mirror, mirror on the wall, who's the fairest, right? And then you can argue, what is the definition of fairest? She's not happy with the definition that's used because it's not fair. What should we decide as our definition to be the most irrational? Well, I know given any irrational, I can approximate it by rationals, and I can get at least as well as 1 over q squared. So maybe the way I'm going to measure how good of a job I can do is by the size of the denominator. So for a given level of accuracy, how big of a denominator do I need? And if I have 2 different irrationals, and to get the same level of accuracy, one of them has a bigger denominator than the other, I'll say that's harder to approximate. The smaller denominator I can get away with, the better you are to approximate. The larger the denominator, the worse you are to approximate. So anybody want to guess? It is a number you should hopefully have seen, is the most irrational of all. Anyone want to guess? Yes. Do you know why? So the golden ratio wins. This is the hardest number to approximate by rationals. The denominators have to be larger than anything else. And so I'm just going to put this here. How many of you have seen continued fraction expansions? Okay, so if you've seen that, the continued fraction expansion of the golden mean is all 1. So when you truncate it, it's the worst. So I don't want to go into too much detail right now. Again, part of this is to just put some things out there. So if there are things you want to hear more about for the classes we have in early December, these are things we can talk about. But there are ways to quantify how irrational some number is. The golden mean turns out to be the worst. But if you want to approximate it, it's got to be bigger denominators than anyone else for the same level of accuracy. And when you're doing your computations, that can cause problems. Skip this stuff. This is the proof. This at least allows you to pause it. Allows you to solve things. I'll skip this stuff. And I'll just end with going back to what you might do in a second abstract algebra class. So we might be concerned about whether or not a function has repeated roots. We might be concerned about whether or not a polynomial can be factored. And when you're trying to factor it, what are you factoring it over? Every polynomial can be factored over the complex numbers. But then you're not going to have integer coefficients. And so if I want to factor a polynomial with integer coefficients into polynomials with integer coefficients, are there any nice ways to tell if this can be done or not? And there are tests that you can do. And a lot of it depends on what you're looking at. But one thing that's really nice is if you have a repeated root, not only should alpha be a root of f, but what should alpha also be a root of? So it's a function related to f that we've seen many times today. What's a nice function related to f? F prime. So if we have a repeated root, say f of x equals, x minus alpha to the k times g of x, then f prime of x is going to be k x minus alpha to the k minus 1 g of x plus x minus alpha to the k g prime of x. So if alpha is a root of f, alpha is going to be root of f prime. If, it's a repeated root. So if alpha is a repeated root of f, if k is at least 2, so we'll assume k is at least 2, then we actually know that it has to be a root of f prime. If I give you a polynomial, we can define the derivative map without knowing calculus. Right? What should the derivative of x squared be?
2x.
2x. What should the derivative of x cubed be?
3x to the second.
3x to the second. So we can actually formally define, the derivative in these situations. And so there's a lot of tools we can use to tell if a function has a repeated root. And so we just have to ask if f and f prime, could they both vanish at some place? And there's tools and techniques to do stuff like this. It turns out for some of the stuff, the intermediate value theorem becomes quite useful. The mean value theorem becomes quite useful. And so I'll just mention this result. So if alpha is a real algebraic number of degree d, then it's approximable to rationals by order at most d. What this means is if I want to look at alpha minus p over q, if I want this to be less than or equal to some constant, depending on alpha, over q to the d, is it possible to do that infinitely many times? And if the polynomial if the root satisfies a polynomial of degree d, it can be done to order at most d infinitely often. It can't be done to order d plus 1. So this gives me a chance to revisit the necessary versus sufficient. What is the difference between necessary and sufficient? This is something you should all know. And it's so hard to say this without thinking of the movie Dodgeball. Please tell me people have seen that. So what's the difference between necessary and sufficient?
Necessary is, this is required for this.
This is required.
Sufficient is, if this is true, this will also be true.
Right, but it might be possible to get to the same result without going through that. So this says it's approximal to order at most d. That doesn't mean that it can be approximated to order d. It just says you can't do better than d, but you may not be able to do that well. And so Liouville's number. This is a number that you should see. It's the sum, n goes from 0 to infinity, 10 to the negative n factorial. Well, let's do 1 to infinity. So this is going to be 0.1, and then the next one, when n equals 2, I'm going to have 1, and then the next is going to be 10 to the negative 6, 1, 2, 3, 4, 5, 6, and then I'm going to have a bunch of zeros and then a 1, and then an even longer bunch of zeros and then a 1. This is really sparse, and because it's so sparse, if you approximate and chop it off here, the error you make in chopping it off is really small because things are going at a factorial rate. This number is extremely well approximated. In fact, it's so well approximated, you can prove that this number is transcendental. So again, if this is something that you're interested in, it's not too bad to prove that this number is transcendental. You can show it can be approximated to order d for any d. And by Liouville's theorem, we know that you can't do better than d if you're root of a polynomial of degree d. Since this can be done to any level, it can't be algebraic. So this is a nice number to prove is transcendental. All right, so this just gives you a little bit of a flavor of some of the infinities, some of the structure of numbers. When you do a lot of things in mathematics and physics, the structure of the number often governs the dynamics. And it becomes important to know. We saw this when we were looking at certain rings. Was alpha a quadratic irrational? Was it a cubic irrational? And that can impact the structure of the ring that we're looking at. When we're looking at things like Benford's law, how close is a power of it to a power of 10? That can affect the rate of convergence of the bias. So these questions are really important. at the end of any semester, it's nice to talk about what comes next. Where do you go if you continue in the subject? This is an introduction to modern algebra. It's done with what is being done in modern algebra. A huge part of the subject is trying to find roots of equations. Roots are hard. So one of the big results you would prove in the next class using Galois theory is that if you want to solve things with, radicals and the coefficients of the polynomials and have a nice closed form, once you hit degree 5, we can't do anything for the general case. Degrees 1, 2, 3, 4, we can write down the solution. And we saw the solutions for 3 and 4 were painful, but they're explicit, they're doable. Once you hit degree 5 and higher, you can't do it in general. And so you have to start talking about approximating. And you can ask, how good is your approximation? How well can you work with it? How much of an issue does it make? And so I'm going to just stop here. And I want to say something afterwards.